I'm Ben-Yaakov. This presentation is entitled Combined CCM-DCM Average Simulation of PWM Converters, and this is an LTspice implementation. So the problem we are addressing is a PWM converter, which is a switching device. There are switches here, power switches, and then we have some feedback, control. We have a modulator, which produces the pulses to the gate. And the objective here is to translate the switched assembly and the modulator into an equivalent continuous circuit. Could be nonlinear, however, that it can be run on a SPICE-compatible circuit simulators, both for transient analysis and AC analysis. To do that, we first recognize that all basic PWM converters, buck boost and buck boost, share the same cell here. We call it the switched inductor. We have an inductor which is switched between 2 points. I call them B and C. B is where the switch is. And then there is an active, this is D on this path here. And then we have a diode, which is in fact also a switch. So all of the PWM converters are basically based on these three configurations, which are only different in their orientation. The basic cell is the same. So it comes to reason that the same model will apply to all PWM converters. Now, other topologies like half bridge or even a flyback are actually derivative of these topologies. So we have a switched cell here, the switched inductor, which we can represent by two switches here, the on and off. B is where the on is. There is also a third position, which is an open one. I'll talk about it a little bit later. And this is for DCM, for discontinuous conduction mode, where the inductor is not connected to any active voltage sources, so there is no current in it. The objective here is to take this thing and convert it in something which is continuous. It has 3 ports with 3 currents coming in or out, like the A, B, and this is the convention that I'm using. A is coming in and B is going out. Of course, you can have then a negative current. And then we have, of course, the inductor, which is exposed to the average voltage, generating the average current, which is then translated into these current sources depending on the duration at which the switch is on in each one of these ports. Okay, so this is the idea behind the average behavioral model of a PWM converter. Just in an illustration first, if I have a buck converter, we have the inductor here, here's the inductor, here's the 2 switches. And in order to do the simulation, or first of all, the conversion to a behavioral average model, what I do, I first of all put here a dependent source which represents the average voltage here. And the average voltage here is here V in times D on, the average voltage here. And then, if I want, then I can load the input with the average current, which is in this case also IL, this is the inductor current, times D on. So this generates the current, and then the current is translated here to a current source, and here it is. So what I see here is the typical transfer function of in this case, a boost converter. We see this is the gain, this is the phase. Now, a boost converter has a right-half plane 0. So I have here a deflection and then a phase shift of 180 degrees due to the fact that this is a second-order system. And then I have a right-half plane 0 proportional way to load the input. So this is the basic idea behind the average behavioral model. In the case of simulation, in the case of SPICE, we do have to worry about translating everything to something that SPICE will understand. And in particular, we have a problem with d-on. D-on is a parameter which could be changing, could be DC, AC, time dependent. This is something that SPICE does not recognize it, so we sort of decode it into a voltage. So there'll be a node in the system, we'll call it d-on, and the voltage of this node represents the duty cycle. So then I can have a current source, which is the current of the inductor, times the voltage of d-on, so this is in fact IL d-on. So this is how we translate this behavioral model into a SPICE compatible model. Now this is a large signal which is appropriate for transient analysis. AC analysis is a phasor calculation. So if I have a nonlinear source, like a product of two variables, this is nonlinear. So what has to be done is to linearize it. So LTspice, as well as many other simulators, which are, say, based on the original SPICE or some other engine, do have the capability of doing this linearization. This is done automatically, transparent to the user, doesn't show up, and it entails taking the differential, that is the partial derivative of the function, with respect of each of the variables. So in this case, it will be the partial derivative of this thing, the V out, with respect, say, to this variable or this parameter, and therefore we are getting a constant times the AC component or the phasor component in the two cases here for the two derivatives. Now, in the case of a numerical simulator, of course, this is done numerically. So we are talking about the difference, the ratio between differences. Okay, this is the local derivative, and this is the AC component. So what happens is that rather than having one source, we have now two sources. These are linear sources because this is a constant times the variable, a constant times the variable. So we can now carry out the phasor analysis. So let's take an example. This is a boost converter. I have here the input. This is the inductor. This is a synchronous configuration, two transistors, the output section, and we know that V out to V in is 1 over D off. D off is 1 minus D on. This is for CCM. So now I'm translating this circuit into the average behavioral circuit and doing it in an intuitive way. First step is to take care of the average voltage across the inductor. Here, V in, I don't have to do anything because this is already DC. Here, I can take the average. The average is D off times the out, because D off is a fraction of the time that I'm spending here, otherwise it's 0. So therefore, this source here is V out, which is the output voltage here, times VD off, voltage of D off, which represents D off. And then I have the output section fed by a current source. And again, this current source, this is the current going here, the average is the inductor times the fraction that this is on, which is D off. So therefore, this is IL times VD off. So this is the current source. Then I have the voltage source representing or generating the D on node. And then I've defined D off as 1 minus D on. Okay? So I'm running now a transient analysis and stepping the D on from 0.1 to 0.8 with 0.1 steps. Okay, so now this is the simulation. I see the values for different duty cycle going up with the duty cycle. And then I'm using the measure function available at LTspice, which is sort of summarizing the parameter sweep and giving out the output as a function of the swept parameters. So here it is. This is the duty cycle, which has been swept from 0.1 to 0.8, and this is the output, and you can see very nicely the behavior of the boost, 1 over d off, or 1 over 1 minus d on, which is typically nonlinear, of course, and looks like that. Now, what about AC analysis? So first of all, I have to define the AC analysis itself, and then I have to have an AC source, and I'm putting here as the d on. So this is a small d, it's 1. So it's simplified thing because then the transfer ratio between duty cycle to output, you have to divide it by 1. And then I'm defining d off as 1 minus the voltage here. So whenever you have a change in the duty cycle here, it will translate to, actually it will be minus, same number, only with a minus sign here. And then everything else is the same. There's no change. And here it is. Very typically, we see the gain, the solid line, and then we see the phase. Being a double pole second order system, we have a 180-degree leg, and then due to the right half plane 0, we have another leg of 90 degree, so it comes out to be minus 270. Note, however, that this is transparent to the switching frequency, so strictly speaking, this is correct only for frequencies below half the switching frequency because of the Nyquist sampling theorem. Actually, it's less than half, so one has to be aware that at very high frequency, this is incorrect or irrelevant, I should say. Now, I'm adding here now a ESR to the capacitor. This adds a 0, a left half plane 0, and here it is. So what we see here is that we have the 180-degree leg, but then we have both the right half plane 0, minus 90, plus 90 due to the left half plane 0. So these are canceling each other, so eventually it comes back to minus 180. So as we can see, the AC analysis is really handy and operates very well. And what about discontinuous current mode? Well, it is a little bit more complex here, but let's see how we can derive it first, and then once we derive it, of course, if you have the answer, then you don't have to worry about all this derivation and the analysis that I'm showing here. But let's just go over it very quickly. In this case, the problem is that the current goes down to 0. Consequently, the T off, what we call, as opposed to T of prime, is smaller, okay? Because the current goes down to 0 here. T of prime is 1 minus T on, okay? This is. But here, it's a different value. So there are two things we have to worry about. First of all, what is the impact of this on the average inductor current? And secondly, how to derive this value, which is important. As far as the inductor voltage, things are the same, except that I have to take into account now, when I multiply the voltage times D on and then D off, I have to use the correct D off, okay? This will be okay. This is T on, T off over the period, and this will give me the average, which is okay. But, of course, for that, I have to know what is T off. Now, as far as the current sources are concerned, again, the T off is shorter, so the average inductor current is not half point here of the peak, it's somewhere lower because there is a void here, there's nothing here. And as it turns out, there is a correction you can do by taking the normal or CCM average and divided by D on and D off. D off now is not 1 minus D on, it's smaller. When it is, that is in CCM, then this becomes 1, so everything is okay. So this is a correction for the current. So now, if we look at this model, we have the inductor current coming in, And then for the two sources, we have to normalize them or correct them for the fact that now T off is smaller than 1 minus T on, minus D on. Okay, D off is smaller than 1 minus D on. Okay, so these are the sources. And now we come to the question, what is T off or D off in DCM? Okay, and I'll not go into all these derivations, just the end result, and here it is. It turns out that D off is equal to 2 times the average current of the inductor, L is the inductance, F is the switching frequency, VAB is the voltage between ports A and B in the model, times D on, and minus D on. So this is D off. Now, D off prime, which is this in CCM, is 1 minus D on, and as we can see, this D off that we have calculated here is smaller than this value here, which is very important. So now we're ready for the combined DCM and CCM model. Basically, the configuration is the same. There's nothing different. We have an average voltage on the inductor, we have current sources, but the definition of these are different. This is the definition for the current sources. This is the definition of the voltage across the inductor, while this is D off, which is calculated from this equation. But I've now added a feature which is available in most simulator, and that is a logic decision that D off is the minimum between the D off of the DCM or 1 minus D on. So while running, the simulator will pick up the correct D off depending which one of them is the smallest. Now, in the case of CCM, this comes to be larger than the D off, the normal D off CCM, okay? So this will be the smaller. In the case of DCM, this will be the smaller, and it'll take the smaller. So here it is, and let's have a look now at some example. We have now a buck circuit. This is a buck circuit. I'm identifying the A, B, and C here. B is when the switch is on, the D on, and this is C. In this case, I'll assume the voltage on the diode is 0, and this is why I've put here a short. You can take into account the diode. I'm not doing it now. So C, this is assumed to be like a synchronous, say, buck with 0 RDS on. So when conduction is in this path, it goes down to ground. So now we have this load. Here is the load. I've added an ESR to the capacitor. This is the inductor, capacitor. This is now the current source, which is feeding the load. This is the inductor. This will be the average voltage on it. So this is in a formal way when I have defined A, B, and C. And then I have here, of course, the voltage source, which is loaded by this current, which is D on times IN, and then corrected for DCM. So this is now ready for DCM while corrected for DCM. Now for that, I have to do the following. First of all, generate a source for D on, and then define D off, or the source of D off, as the minimum of all this expression here that I've shown before. Okay? So this is just translating this into the LTspice syntax. Okay, so it's just one-to-one translate. And now I'll be running a large signal in which I'll be stepping the load while keeping the duty cycle constant. Okay, the duty cycle is constant, and I'm stepping the load. So in this case, here is what I see, and then using the measure option here, I get the output voltage as a function of the load resistance. And as we can see, up to say 21 approximately ohm, it is CCM, and the duty cycle is constant, independent of the load. Here, well, the resolution is not good enough, but here it's starting to change. And typically, as the load resistance goes up, the voltage goes up. So this operates very, very nicely. Now, what about small signal? Okay, when the load is 10 ohm, I can see the second order very nicely as before. This is now for buck. And when the load is 60 ohm, I see the DCM response. It becomes a first order, so to speak, and therefore the phase shift is only up to minus 90 degrees. And this is all consistent with all what we know. What about closed loop simulation? So here is an example of a boost. I've constructed here the model in a less formal way, knowing that what I have to do is just the average voltage on the inductor. So I have on one side V in, okay, and then on the other side I have D off times V out. This will be the average voltage on the inductor, the boost converter. Here it is. The voltage here will be the output voltage times D off. And then I have the output section. And then this will be the current source of the output section, which is the inductor current times VD off as before. And then we have the duty cycle, and then D off is 1 minus VD on. Again, this is for CCM. So in closed loop, what I'm going to have is sensing the output. Here is the compensator, and then this is the duty cycle generator. In CCM it's simple, in DCM it's a little bit more complex, and then we have a driver to the transistor. So here it is, what I came up with, and what I see here is this is the boost converter, and here is the compensator. I built it around a operational amplifier. This is a divider. I have here, this is 5 volt, so this is 2.5 volt. So here this divider brings the output voltage to 2.5 volt. And then here is the simple compensator, just a simple pole, first order, like type 1, you might call it, while the breakpoint is determined by the resistor, of course, and the capacitor. So here it is. This is the compensator. Again, this is the divider, 2.5 volt. And then we have here the compensator. So I'll have a lag type of a system, but then I'm passing it through a clamp. This is now a clamp made by a behavioral source with a table that will limit the duty cycle. This is in order to avoid some convergence problem, because the system might lock into some imaginary or some unrealistic duty cycle, and it'll be very difficult for it to return to the right operating point. So it's a good advice to limit the duty cycle to the real boundary. Now the excitation that I've put is in here. This is in the path of the feedback. This is the AC excitation. Now I can look at various parts of the system, partial transfer function, and let's have a look first of all at the transfer function between D on and in. This will be the compensator transfer function, and it's a first order, as you can see it here. At very high frequencies, some things seem to be changing because of the amplifier, okay? So this is the range that the amplifier is okay, and I can see here, this is what I'm interested in. I can see here typically a first order, and this is 90-degree phase shift. This is fine. Now, I like to look at the loop gain, okay? Loop gain can be looked at if you can get the ratio between the output here and the input here around the reference. In real systems, it's very difficult to identify these two signals, because if you look here, okay, you have here a whole combination of the input and the reference, and it's not that clear what is in and what is out. So in order to avoid this, what we can do, and this is normally done, we're going to generate another junction here, which is kind of very clear, that we can from it get this transfer ratio, the loop gain. And this is done by adding here another junction. So this will be another excitation. And so in this case, obviously, if I'm generating this thing, then the ratio between out prime to in prime is the loop gain. This, in the case of simulation, can be done by adding an AC source in series, okay? And then, if I look here, this is exactly what I did. I've put here an AC source in series. I've also added, by the way, a step for transients, so I can look at the response to a load change. But here I have this AC, and if looking at the two sides of it, this will be the out and this will be the in, and the ratio between them is the loop gain. So now I look at the ratio of out AV to V in again. This is here and here. This is like the in, and this is all the way up to here. And here is what I'm getting. So this is the loop gain, and 0 dB is here, and this is the phase shift, which is not that hot, okay? And indeed, if you look at it, that's what you see, that we have quite a bit of a overshoot. This is, by the way, due to the right half plane 0, and then we have this overshoot. So another way to look at it, in a more, I think, interesting and perhaps useful way, is not just to look at the border plot, but look at the Nyquist. And as it turns out, LTspice has this option built in very nicely. So as you go to this window, you just change border to, this is, you right click here, and then you go to this window, and then you change it to Nyquist, and here is what you get. So this is the Nyquist of this transfer function, which is very, very nice. This is the real part. This is the imaginary part. Here we are. This is the 0, of course, here. And then this is the -1. And as we know, encircling the -1, 0 is indicative of an unstable system. This is just a close-up of this thing. We see here, this is the 0, here, 0, 0. This is the unit circle. It looks like an ellipse because of the scaling here, okay? And then this is the loop gain, and we can see that it misses this encircling here by just a little bit, okay? And this is for a 3 nanofarad capacitor in the compensator. So now if I change it to 10 nanofarad, here is what I'm getting. It's farther away, so the phase margin is larger. Of course, we can look at it in the body. And this is as compared to the previous 3 nanofarad, okay? So by increasing the capacitor, I can improve the phase margin of the system. So here it is in the time domain. This is what we got with the 3 nanofarad. This is the overshoot. And here you see very nicely the smooth response with the 10 nanofarad. So we can see that this simulation tool really works very nice. So this brings me to the end of this presentation. I thank you very much for your attention. I hope you find it of interest, and perhaps it will be useful to you in the future. Thank you very much.